Welcome everybody, my name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm, and today we're going to continue with the introduction to machine learning methods. In particular, we're going to look at several SVD related approaches. We're going to focus on the method of snapshots, and we want to also continue with the meaning of the different correlations that you can find on the data, which we started last week. So let's go right into it. If you remember, last week we were talking about the columns of U, which are actually, if we call them Uj, remember these are vectors, are eigenvectors of this product matrix, eigenvectors of x times x star and the columns of V and this we're going to call Vj. These are eigenvectors of x star times x. Okay, this is where we left it in the last class. Now I would like to emphasize a bit more what this means in terms of the interpretation of these terms. These columns, both of U and V, they are actually connecting to the correlations in the data. So they capture. I moved to blue. Remember that the red stuff is the ending of the last video. Now we start with new things for this week. These precisely capture correlations in X. In particular, there is a very nice connection between the singular values and the eigenvalues. Remember, and we mentioned it a little bit in the last video, but today we emphasize it a bit more. They are basically related to the eigenvalues, which are sigma j squared. So the singular value decomposition is basically applied to matrix X, and that gives us singular values. The eigendecomposition, that would be then connected with the correlation matrix. So basically things that come with patterns and correlations of X squared, and then there we are talking about eigenvalues. So there is a connection between the eigenvalues and the singular values. At the end of the day, sigma j squared give us the eigenvalues. This is a very important concept to be able to interpret a bit better what we are doing with these methods. And right now, I would like to see how can I apply this in practice. I have a very large data set. I maybe don't have as much data in time as I would. Maybe the spatial resolution is not ideal. When it comes to applying this in practice, in real cases, we're going to be looking at what is called the method of snapshots. So in the method of snapshots, and this is developed by Sirovich in 1987. Sirovich, 1987. Okay. In the method of snapshots, we're going to consider a case where N, Norway, is much larger than Madrid. Remember, that means that we have a lot of spatial resolution, but not so much temporal information. We have a tall and skinny matrix, which is a typical case of what happens in CFD. In CFD, you have very high resolution. You don't always have as many samples as you would like in time because of the high cost of the simulation. Remember that experiments typically are the opposite. You don't have so many points in space, but you can afford to have very long time series, and therefore that's kind of like a different and closely related problem. So let's assume that the data matrix has the property that Norway is much larger than Madrid. Remember, this is the case of CFD, where resolution is high and number of snapshots lower. And again, this is in general. Of course, there's cases in CFD where you have many snapshots. This is kind of like an example of a DNS where classically you would not have the computational power to iterate for very, very long. You just try to see how much you need for convergence, but you would have then the spatial resolution. So in these cases, you have the following. Let's move to the next screen so we have more space. We're going to have the product x star times x. Okay, and this is actually interesting, right? If you remember, matrix X is going to be Norway times Madrid, and therefore matrix X star is going to be Madrid times Norway. If you multiply these two matrices, what's going to happen? Well, this product is going to be Madrid times Madrid. If Norway is much larger than Madrid, this matrix is going to be much smaller than matrix X, right? It's much smaller than X. Okay, remember that X would be Norway times Madrid. This dimension is the same in both cases. This one is much smaller than this one, just because we are assuming that Norway is much larger than Madrid. Therefore, it's more interesting to work with X star times X than with X directly. Now, this is interesting because we can do the following. We can work with this matrix with X star times X, meaning that we can use this property. We can use this to find the following. Vj and sigma j. And now remember, sigma j are the singular values, nothing strange or surprising with that. Vj would be the columns of the V matrix. These are the so-called right singular vectors. Okay, let me just define them. This Vj, these are the right singular vectors. Okay, I will get to that in just a second. Before, I want to tell you a bit more about how to find the uj, so the columns of u, which would by symmetry turn out to be denoted as the left singular vectors. So let's go there and then I will just explain you a bit more about how to interpret all this. So the left singular vectors these are uj, can be obtained as follows. Okay, so these ones can be obtained by using the properties that we know, because the product x times v. So basically, I'm post-multiplying the data matrix with the V matrix, basically. So x times V, if now I apply the SVD, so I know that I can expand x, I'm going to have U times sigma times V star, and this is times V. Remember now that this X matrix can be expressed like this, U sigma V star. So this is essentially the singular value decomposition, the SVD. So since lecture number 1, we have been using that equation. Of course, the product of V star times V, that gives me the identity matrix, right? So this is the identity. And remember that we're using this trick is what we do all the time. No, we're just finding ways by expanding matrices here and there to find the product of V star times V, U star times U. So things get simplified, right? And that allows us to really use the matrix properties in order to find good, meaningful equations, basically. So that becomes the identity matrix, which means that I can now write that xv is equal to U times sigma. Okay, this also means that I can write the following. The matrix X multiplied by the columns of matrix V, that would be the Vj. This is going to be equal to the Uj times sigma j. And these are, of course, scalars, right? So essentially what I'm doing now is that I am expressing matrix V in terms of its columns and matrix U in terms of its columns as well. And taking the entries of the diagonal matrix sigma, I just take the singular values, right? So that's, again, no dark magic or anything. I'm just using the properties of the matrices with simple linear algebra relations. So I have that, and that means that I can now get the entries of the matrix U. Because from this relation, remember, by using the matrix x star times x, I can obtain the right singular vectors and sigma j, which is this value and these values. Of course, the matrix x is the entry, is the data matrix. So from this equation, I can resolve my uj's, which is what I want. This would be the left singular vectors, which are precisely the entries of the U matrix. Now, from that equation, we can get the first m columns of U. This is the key. The key is first m columns. Because remember, matrix V, right, is going to be a smaller matrix. It's going to be Madrid times Madrid, which means that here we cannot get more left singular vectors than m. But this is actually, this is still okay. I mean, let's imagine that we don't have a super long time series. Then, of course, the matrix V is going to be limited by the Madrid dimension, right? We're going to have as many entries and columns in V as Madrid. That means that with this method, working with x star times x, we will get the V matrix, which has m entries, and that will allow us to only obtain m entries of U. So this is basically what we get here. This is why it's called the method of snapshots, because I can use, even if I don't have an infinitely long time series, I can use the Madrid number of snapshots that I have to try to have a meaningful representation of our data. The longer the time series, the better, and the more complete U matrix that we will get. If the time series is shorter, that means that we will have fewer modes in our U matrix, fewer columns, and that means that our data will not be as converged, it will not be ideal, but in principle, we are extracting the best that we can from the data that we have, okay? I will just write a couple more definitions and I will tell you more about interpretations. We remember that where M, which is Madrid, is the number of snapshots. Now, in fact, these values over here, these are the left singular vectors. The UJs, these ones, would be the left singular vectors. Good. In the next video, we're going to be talking in detail about a method called proper orthogonal decomposition, POD. People who are more familiar with fluid mechanics know a lot about this method. They maybe have heard too much about it. You're going to see that the foundation of the SVD, of the singular value decomposition, is actually very useful to calculate the POD, the proper orthogonal decomposition. In practice, what you want to do with POD is decompose a spatiotemporal signal, like the fluid flow data, into something that is purely depending on space and something that is purely depending on time. The stuff that is depending only on space, those are the spatial modes. And the things that depend on time, those are the temporal coefficient of those modes. In practice, what we will see is that the left singular vectors, the entries of uj, will be the spatial modes, and the right singular vectors, also scaled with the singular values, those are going to be the temporal coefficients. Okay, so in the next video, when we talk about spatiotemporal decompositions, which is basically the POD method, we will really get into it in a lot of detail. But for now, keep in mind that the SVD is an integral part of the calculation of the POD, in the sense that the left singular values will actually become our spatial modes. The right singular values scale with the singular values themselves. The right singular vectors, scale with the singular values. Those will be the temporal coefficients. Okay. Before going there, I would like to spend a few minutes talking about methods related to SVD. I already introduced the POD, but there are other methods that are very relevant when we are talking about this very powerful method, which is the singular value decomposition. So let's go and try to look at some of these methods. This is what we call, well, related methods, basically. So SVD is an integral part of a number of methods. For example, we are talking about the principal component analysis. Also called PCA. And this is a method that is very, very widely used in statistics and machine learning. In general, these methods are actually quite similar. They share the foundation, which is the SVD. Depending on the community that you are reading for your papers or that you're discussing with, at the end, we are talking almost about the same thing. So if you read in some book or in some paper, PCA, principal component analysis, don't get scared. This is something that is essentially the SVD, and everything that you learn from the SVD will be helpful for you to understand the PCA in a number of flow cases and a number of problems. In particular, in the ML community, PCA is the term that is used all the time. But of course, in mathematics, in linear algebra, is actually the SVD, what we are talking about. The other method that I already introduced is the proper orthogonal decomposition. Also known as POD. This is in fluid mechanics. So for the people who work with fluid mechanics and who like fluid mechanics, this is something that they have heard a lot of times, POD. In the next video, you will see all the details about it. There is another way, which is the canonical correlation analysis. The CCA. And another one very important is the Karhunen-Loew transform. So the Karhunen or also called KLT, which is very widely used in probability theory. Now, there is yet another thing that is important here. Sometimes data we're looking at exhibits periodicity, and that periodicity is a property that mathematically is very attractive, is very appealing. We have studied since we are in middle school and even before about trigonometric functions and how they're periodic. This is something that can be exploited when our data exhibits that periodicity. So let me also talk a bit about that. Sometimes, for example, data with periodic behavior, it is easier to replace the singular vectors with generic functions. And what are these generic functions? They can be, for example, Fourier modes. And here we are talking about the Fourier transform. Fourier transform FT, which is also a very, very, very widely used method that everybody here probably knows. So I want to highlight a couple of things. First of all, when you do this analysis on periodic data and you do the SVD, those left singular vectors are going to end up being periodic functions. They're going to be sines and cosines, basically. So Fourier analysis becomes the relevant method there. This means that if you know that your data is periodic, then Fourier analysis will help you, and that will be probably the best way to go to encapsulate the information in the most compact and efficient way. Effectively, the singular value decomposition is a generalization of the Fourier analysis to more complicated data patterns. So if the data is not periodic, the left singular vectors are basis functions that are tailored to the patterns encountered on the data. This is actually very interesting because this also means that singular value decomposition will converge with some work, but essentially will become Fourier analysis if the data is going to be periodic. Another thing to keep in mind, you should always embed in your model any information that you know about your data. This is something that I mentioned in many of my videos and many of my lectures. If you try to learn some physics with a machine learning model, and that physics is known, you're going to have an ML model that is not learning the physics to the same degree of accuracy that you would like to have if you would impose those physics. And even if you would reach that level of accuracy, you're wasting computer time because you're using a lot of resources to learn something that you already know. Therefore, you need to embed in your data any information that you know and any information that you have about your system. Just give clues to your ML model. Don't let it discover everything blindly. We know we are scientists, we are students, we are engineers, we're researchers. Whatever we know about our data needs to be embedded in our data-driven models. That will become a very much better practice. It will lead to models that are more sustainable in terms of the training data and more accurate in terms of the type of accuracy that you can get. Therefore, for example, if you know that your data is periodic, use Fourier modes and don't try to tailor a basis that will be less efficient and it will cost you more to learn the periodicity which you already knew. Okay, so this is in general a good practice, a lesson when you're building data-driven models, and keep in mind that this is a principle that will help you when you're working not with these simple models, but with something much, much more complex. So that's all that I had for today. Next time we will really talk about POD and we will focus on POD. For now, thank you very much for coming, for your attention. More videos in the coming weeks, and always happy to receive your feedback and your question. See you next time.